All right, in the case of problem number 7, okay, we have y double prime plus 16y is equal to 0. And again, just taking the terms from the second order derivative as well as for what we have in y in the problem. And if I look at combining the terms in the same degree, we have 2c2 and 16c naught as our constant terms. We have followed by the first order variable terms and putting in factored form as well as x squared and higher. And now we're looking for the solution, okay, to y. And just for what we have right off the bat, okay, we have 2c2 and 16c naught is equal to 0. And if I put c2 in terms of c naught, okay, now we have that c of 2 is equal to negative 16c naught. We have over 2, and right now we'll say that we have negative 16 to the first c naught, and we have all over 2 factorial. And for what we have for the first order terms, okay, we have the coefficients. We have 6c3 and 16c1. Adding those together, we have equal to 0. And we have that c of 3 is equal to negative 16 c1 all over 6. And we have, in this particular case, right, so we have negative 16 to the first c of 1 over 3 factorial. And if I were to continue, so I have 12c4 plus 16c2 is equal to 0. And here I had that c of 4 is equal to negative 16 over 12 c of 2. And then writing c of 2 in terms of c naught, we have negative 16 times negative 16. So we're going to have negative 16 squared c naught. And 12 times 2 is 24. And this is going to be 4 factorial. And if I were to go out even further, and so we will have in the setup, okay, so we have with our c of 5 coefficient, okay, so you have 20 c of 5, and we have plus 16 c of 3 is equal to 0. And here we're going to have c of 5 is going to be equal to negative 16 c of 3 over 20. And we're going to have, in this case, we have negative 16 squared c of 1. And we have 20 times 6 is going to be 120, so that would be at 5 factorial. And now we have a bit of partitioning that is done. If you notice, we have terms in terms of c naught and those in terms of c of 1. And now for what we have for even values, in other words, where we have c of 2, c of 4, it's going to turn out that right now we're going to have like c of n is equal to negative 16 to the n over 2. And we have all over n factorial. And if I were to follow through, say if I have letting n be equal to 2k, okay. So we're going to have in the process, okay, so letting n be equal to 2k, we have that c of 2k is going to be equal to negative 16 to the k. All right. And, oh yeah, so you have c naught in the mix. Okay. Then we have all over 2k factorial. And just partitioning out. Okay, so we have negative 1 to the k times 16 to the k c naught. We have all over 2k factorial. And if we follow through, okay, now 16 is going to be a perfect square. You know, like 16 to the k is equal to 4 squared to the k, and that will come out to 4 raised to the 2k. Right. So we have in the rewrite, so we have negative 1 to the k, and have times 4 to the 2k c naught, and this is going to be all over 2k factorial. Okay. Now for what we have at the other end of the spectrum, okay, for the odd values. Okay, so we have for odd values n plus 1. Okay, so we have for odd values n plus 1. Okay, now we're going to have that c of n plus 1 is going to be equal to, in this case, right, so we still have negative 16 to the n over 2. This time we have c of 1, and this is going to be in the denominator, so we have an n plus 1 factorial. And so if we let n be equal to 2k, all right, so we're going to have c of 2k plus 1 be equal to, in this case, we have negative 16 to the k. We have times c of 1. And this time we're going to have all over 2k plus 1 factorial. Okay. And we have just in the follow through, kind of like the conversion we did and splitting up. So right now we have negative 1 to the k, and we have times 4 raised to the 2k c1, and we have all over 2k plus 1 factorial. Okay, and what I'm going to do here is that to get the degree 2k to match up with 2k plus 1, let me mention, okay, so you have 4 to the 2k, and this is equal to 4 to the 2k plus 1 over 4 to the first. So you're going to have at 1/4 of 4 to the 2k plus 1. So we have just in following through, and just reveal how we got to this particular set of terms. All right, so we're going to have, so you have 1/4 times negative 1 to the k, and now we're going to have times 4 to the 2k plus 1, and we have times c of 1, and we have all over 2k plus 1 factorial. Okay, so this is what we're going to have for our even and odd subscripted values in the constants. Okay, so going back to our general solution. So you have for y of x. Okay, so I have, again, have n equal to 0 to infinity. And we have of c of n, x to the n. And if I partition out separately what I have in k, all right, so we have summation So k going from 0 to infinity. We have a c of 2k times x to the 2k. And for the odd subscripted and power terms, so have k going from 0 to infinity. And we have a c of 2k plus 1 times x to the 2k plus 1. Okay. And we have, upon substituting what we have for c of 2k and c of 2k plus 1, okay, what is going to arise in this case? Okay. And I can just go ahead and extract the constants. So we have c naught, and we have times the summation as k goes from 0 to infinity. And we have negative 1 to the k. And now we got 4 to the 2k times x to the 2k. And we have all over 2k factorial. And we'll have 1/4 of c of 1 times the summation as k goes from 0 to infinity. And we have a negative 1 to the k times 4 to the 2k plus 1. And by then, since I'm looking at, so I have 4 to the 2k plus 1. And now for what we have in this particular regard, okay, so we'll have times x to the 2k plus 1. Okay, we have all over 2k plus 1 factorial. All right, and so just kind of condensing what we have here. All right, so again, so I have c naught times this expression and for 4 to the 2k times x to the 2k, I can go ahead and compile together. So we have times 4x to the 2k over 2k factorial. And we can say that 1/4 of c of 1, we'll just, since we have a constant times a constant, to be a constant, we'll just compress this as c of 1. And we have times the summation as k goes from 0 to infinity. Now we got both 4 and x to the 2k plus 1. So I have negative 1 to the k. I have times 4x quantity to the 2k plus 1 degree all over 2k plus 1 factorial. And okay, and so this is what we're going to have in the Maclaurin series for both of these summations. So we have at the front, this summation will be in reference to the cosine of 4x. Then I have plus c of 1. What I have over here will be in reference to the sine of 4x. And so this will be your overall solution.